This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Good afternoon, everybody. And this week we're going to talk about evolutionary trees. And I have an upgraded laser pointer. That's way better. That's actually 50 kilometers radius, which will be fine for this. So last week we talked about alignments, and the main purpose of alignments was then identifying similarity between sequences. And one of the main purposes of multiple alignments is for building evolutionary trees, for understanding how protein sequences and gene sequences evolve. And for this week, we're going to talk a little bit about how we build evolutionary trees from different types of sources. And just to give a quick overview of what we're going to discuss. So we're going to talk about phylogenetic trees and how they're built and the different approaches for phylogenetic construction that we can divide in basically two types of methods or algorithms. There are those that are considered based on a distance. So creating a distance matrix between pairs of sequences or genes, for instance, and we then create a tree from that. Or those methods that are character-based, that you don't rely on a distance matrix. And we're also going to talk about how do we assess reliability and robustness of these trees. So today we're going to start focusing on distance-based methods, and on Friday we're going to talk a little bit about character-based and assessing reliability, robustness of the generated trees. So over centuries we've tried to classify biological diversity, and one of the main areas to that is taxonomy, which is the science of classifying organisms. So we started really early on trying to find similarities between objects, similarities between species, and trying to rationale why they were so similar. And the main goal of phylogenetic analysis then is to determine and describe the evolutionary relationships between two species or more. And for that we consider theory of evolution and how these species could have evolved. And this is based on speciation events that lead to the creation of different species. And it occurs, well, as a branching process. So you originally have one population of organisms, and they become separated into subpopulations. And later on, and over time, these subpopulations evolve into separate species that no longer can crossbreed. And in phylogenetics, we're attempting to determine the order and the approximate timing of these speciation events to describe their evolution. And this is a very, very simple way to represent them, which is using a tree, especially considering this occurs as a branching process. You start with one species that becomes two subpopulations, and they are then separate physically or not, and then they no longer can crossbreed. So using a tree is a very intuitive way to represent this relationship. And then we can ask questions like how species evolved from a common ancestor. So a phylogenetic tree and classical phylogenetic analysis was based on morphological features. When you think about Darwin going to the Galapagos and identifying similarities between birds, he was looking at, for instance, beak shapes and tried to group similar organisms together based on those morphological features. While these days we have the power of high throughput sequencing, and we can actually use the wealth of biological sequences that have been deposited and created over the years to actually analyze homologous sequences in different species. So regardless if it's nucleic acids or a protein sequence, we can use this information to actually do molecular phylogenetics and understand how sequences evolved over time. And one of the main sources for that analysis is the multiple sequence alignment. So understanding homologous sequences. What's a homologous sequence? What's a homolog? So we discussed this last week. Sequence present in both species. If we use a different word, let's try to use that word here. Sequences that share a common ancestor, right? That's homology. That's a homolog, right? And if you remember, you can have two types, right? When you have, let's say, the same, quotes, sequence in different species, you have what? Ortholog or a paralog? What's an ortholog? Same gene, different species. And paralog?
Different gene of the same ancestor gene
In the same species. So basically, orthologs appeared due to a speciation event, while paralogs occur due to a duplication. So if there was one gene that duplicates the two genes in the same species, and then you have a paralog, right? And then we can identify this information. So the main source of information for phylogenetic analysis these days is multiple sequence alignments, even though they are not the only one. And we'll discuss alternatives today. And so with that information, we can try to find an evolutionary links between organisms and what were the changes that occurred over evolution. And for instance, we can inquire about families of sequences, and that can be useful, for instance, to predict genes with similar functions and how those functions evolved over time. And we can also, as well, estimate time divergence between groups of organisms that share that common ancestor. And a phylogenetic tree, so what's a tree? Let's just start with the basics. Mathematically, what's a tree? Can anybody tell me what's a tree? Anyone? So basically, a tree is a connected acyclic graph. And what's a graph? Can you tell me what's a graph?
It's a collection of nodes that are connected by edges.
Yeah. So what do graphs model? Graphs basically model objects and the relationships between objects. So yeah, you're right. So a graph is a pair G, V, and E consisting of V vertices and E edges or branches that are connected. So that's a graph. So a tree is a type of a graph that we said it's acyclic, meaning there are no paths, there are no cycles. So no paths that start on the first, where the first and the last vertices are the same. Okay? That's basically a tree. And it needs to be connected, meaning there is a path between path, which is a sequence of vertices between every pairs of nodes in that tree. Okay? And we can have two types of trees, phylogenetic trees. We can have unrooted trees, which specify just the relationships between the objects, but not a evolutionary path. And we can have also rooted trees, which will have a specific root that induces a hierarchy relationship between them. Okay? Which will, of course, will have, which will be a common ancestor to all of the sequences considered. And if you consider a path from the roots to the leaves, we will have a evolutionary period of time. And the main parts of a tree, of a phylogenetic tree, will be, for instance, the external nodes or the leaves. So the external nodes would be, for instance, the sequences we are considering, the current day species we are considering, and they always have a node degree of 1. What's the degree of a node? It's a property of the node which corresponds to the number of connection it has. So while external nodes or leaves have degree of 1, the internal nodes have at least a degree of 2. Okay? And for instance, then the external nodes or leaves could be a taxonomic unit, could be different current day species, genes, proteins, for instance. And the internal nodes could be interpreted as the most recent common ancestor of a given set of sequences. For instance, this internal node will be the most recent common ancestor of A and B. Okay? And the node degree for these would be at least 2. Usually 3 for internal nodes. If you have the root will always have a degree of 2. And usually the edge length in terms of a graphical representation of these 3 will be related to the time from one speciation event to the next. Okay? And if you consider the topology, it's basically the branch pattern. So when we say the topology of a tree, we're just considering how these branches are created. Okay? And if we think about it, let's consider then n sequences. How many different trees we can construct with n sequences? And that would be different if you consider rooted and unrooted. Any guess of the order of magnitude of how many trees you can create with n sequences? Quadratic, a linear number? Is it something that we can actually generate all of them and identify what's the best one we want? Not really. So the number of potential trees we can create, it's actually close to a factorial. And that grows quite quickly. So let's say we have only 3 sequences. Okay? There's only one possible unrooted tree for that. But if you consider 10, we have already over 2 million. And that grows really, really quickly. And what about rooted? Is that more or less, if you consider rooted trees? More. Yeah? So you can vary the internal nodes, so you basically have -3 here, which will make a lot of a difference here. So for 10 sequence, we'll have over 35 million possible rooted trees. And that just to say that enumerating every single one of them and trying to come up with a rationale to try to find what's the best one is just not feasible. So again, we need heuristic approaches to identify what's the best way to generate a tree. So the best one, which and approaches to do that would involve then, for instance, finding tree which minimizes the number of changes needed to explain the data is one way to see it, which is called parsimony. So maximizing parsimony is basically minimizing the number of changes I need to explain the data. So how many substitutions I need to do, or insertions and deletions I need to do in the data to actually explain all the changes. And we could also try to also minimize the distance between the different taxa. Yeah?
Is there any maximum number of degrees a node could have?
A maximum number? That depends, let's just go back. In terms of a phylogenetic tree, considering we have a branching process, so one species, we're considering this one species giving rise to 2 new ones, we'll always have up to 3. Right? So that parent node here, so you have, let's C and D, which are external nodes, so they will always have degree 1, and the internal nodes will always have degree 3. That's because it's a binary tree. So if you consider this node a parent, each parent always has 2 kids, this one and this one. So you have 2 edges here and 1 edge from the parent. So you always have 3. So in terms of internal nodes, all of them have degree 3 apart from the root, if you have a rooted tree, which would be degree 2. So you have 3 possibilities, 1, 2, or 3 for a binary tree. Okay? So on week 7, I think, we'll discuss graph theory. And we'll describe all the potential aspects of graphs, trees, and other graph derivations. And we'll discuss, for instance, the importance of trees in analyzing, the importance of degree to analyze a network. But that's later on. For phylogenetic trees, we'll have these 3 possibilities. Is that clear? Sure. Sorry, I thought it would be awesome. Oh, you use that to point stars, actually. It's quite... Is it too much? Yeah. Sorry about that. No problem. I'll go back to the old one. Better? Can you still see it? Sorry, I got excited. You can't leave me with a credit card. I started buying crap stuff. Anyway, where were we? So we were discussing the following. So the number of potential trees we could have, it's really huge. So it's the order of factorial. So this is a product of I starting from 3 to n. So you keep multiplying this number. So it's closer to the big O notation of a factorial. And basically, we need a heuristic to find the best one, and a way to access it as well. And the two ways, as I was trying to say, that we can approach this is trying to, one, use parsimony. So maximum parsimony will describe the minimum number of changes we need to do to describe the data. And if we're dealing with distance, for instance, we can try to minimize the distance between the taxa or the items or the sequences we are dealing with. The basic workflow then for inferring a phylogenetic tree is the following. So we will start saying that we have a common ancestor, and what happens is substitutions accumulate over time, and these substitutions tell us about evolution and genealogy. For instance, we have substitutions here for this ancestor, and then they propagate, and then you have more substitutions, and that's how we end up with the current day species, for instance, or the current day versions of the sequences. And in order to identify that, we usually start with data preparation, which has a lot to do with usually multiple sequence alignments. But there are alternatives to that. And then we go to the next stage, which is tree inference. We need to choose an algorithm to, from the multiple sequence alignment, derive the tree. And there are a few different approaches to that. Those that consider distances, those that consider the actual characters that are present on the multiple sequence alignment, and then we analyze the tree, basically to assess robustness and reliability, and whether the tree that we got is just occur by random. So basically, we'll go from then a multiple sequence alignment, and we'll choose an algorithm, a way to build our phylogenetic tree, and the main thing is which method to choose. So there are different methods, but based on your data, some might be more appropriate than the other. And there are basically two types of phylogenetic reconstruction algorithms. The first class is considered the distance-based class, which basically tells us that the phylogenetic tree is built based on the distance between the items, sequences, genes, or species. And then the more similar ones should be evolutionary, more related. So we try to find the closest ones and put them together on the tree. And for this, there are two main algorithms we're going to discuss, UPGMA and neighbor joining. And there are another class of reconstruction algorithms, which is character-based. And for character-based, every taxon, sequence, or gene is described as a number of characters, let's say in an alignment, or even morphological attributes, and they each have a finite number of states. For instance, each character on a DNA sequence alignment will have 4 potential states. In a protein sequence alignment, 20 potential ones. And the goal is to build a phylogenetic tree that best explains that character matrix. And of course, that involves optimizing objective function, and the two main ones that we'll discuss on Friday are maximum parsimony and maximum likelihood. So if we start then with the distance-based methods to reconstruct trees, they basically use the concept of agglomerative clustering. So let's say you start with an alignment, and from the alignment you're going to generate the alignment scores. And if you calculate, for instance, a pairwise distance alignment, you can generate a distance matrix, which will then describe the similarity between the sequences. And you can start picking and choosing based on the assumption that the closer this score is, the closer evolutionarily the two sequences are. Then let's say you choose a pair to put together. So initially, every sequence starts on a separate cluster, and then iteratively I choose 2 sequences to merge. So how many steps do I need to get the full tree reconstructed? So I need n-1 steps. So we start with n groups. When we merge one pair, we have n-1, n-2, n-3, until we have one group. So this is the concept of agglomerative clustering. So it's an iterative process that we keep reducing the number of groups we have. And in terms of distance metrics, even though the most common used ones are scores for multiple sequence alignments, and these are used, and there are multiple approaches for multiple sequence alignments, as we discussed previously. For instance, we have cluster, which is progressive multiple sequence alignments, which is based first on a pairwise alignment, and also there are iterative and also probabilistic approaches. But regardless of them, if you have a score that will say how similar to any two pairs of sequences are, we can then create a distance matrix. And there are also alignment-free alternatives. They are very important, for instance, for taxonomy classification. And the main one used these days is k-mer count. So basically, k-mer is a substring or a word of length k. And this is quite important for species identification and for also detecting contamination in sequencing experiments. Also important for de novo assembling, and is usually considerably faster than the actual alignment, but much less sensitive. But it's worth understanding what k-mers are and how they work. So a k-mer is a word of length k. So let's consider then two sequences, sequence X and sequence I. And we want to identify all possible substrings of length k. And let's consider k equals 3. What we're going to do then is a sliding window throughout the whole sequence X and Y. So let's say we start with 3, A, T, and G, and we keep moving the window that way. Then we have T, G, T, then G, T, G, and so on and so forth. Okay? What do I do with that? So this is a way to represent the sequence, right? So I'm considering how many of these k-mers each of the sequence have. And for instance, we can then consider the union of all possible k-mers on those two sequences. In this case, we have 4 different ones, and we can, for instance, take into account the frequency of them. And this is a way to go from 2 sequences to their mathematical numerical representation. So it's an integer vector. And with that integer vector, I can then calculate the distance between them. So this is a very, very simple and efficient way to compare 2 sequences without any alignment. And here I'm using Euclidean distance, right? What other kind of distance we can use to compare 2 vectors? Hamming distance, for instance. What's the Hamming distance between X and Y? 3, right? And there are many, many other types of distance. You can use Manhattan, you can use Tanimoto. And regardless of this, the main trick here is going from a sequence representation to quantifying its main components. And that's what k-mers are. So you can count the fraction of unique k-mers, for instance. And in that case, only Y has a unique k-mer, which is CAT. You can also generate a frequency count or a histogram of the k-mers. There are different ways then to represent the 2 sequences. And of course, there are different distance metrics you can use to compare the 2 sequences. And the k size will also affect how you represent them. Yeah?
This method in the previous topic just talks about, is there another one that is more accurate?
I couldn't understand you. Can you speak louder, please?
Of the K method and the previous line method, which one would you say is more accurate?
Either k-mer or
Is,
multiple sequence?
yeah, multiple sequence, right?
Definitely multiple sequence. So k-mer is alternative when you actually have a compromise between speed and sensitivity. For instance, if you're sequencing a lot of data and you need to compare a huge number of sequences, this is a quick alternative. So, but yeah, it's faster than aligning. So what's the cost for aligning? So the cost for alignment is quadratic times logarithm, while what's the cost to computing k-mers? Linear. So it's considerably quicker, so it's actually scalable. But of course, he has limitations. So it's just saying this is the current content, but you can find a lot of false positives with it. But again, it's a compromise between performance and actually sensitivity.
Is it a good idea to, with 3 sequences, use the camera length of 3 and then 7 and then 100 and combine the results?
I believe there are a few methods. For instance, that's quite common for taxonomy. When you try, let's say you have a sample, and you're trying to describe the taxonomy landscape of that, let's say microbiome, soil, or something like that. You want to identify what class, what are the taxonomy levels that are common there. There are different alternatives. So, for instance, I think Dada2, which is one of the main algorithms for that, for taxonomy classification, uses K of 4. But they tested different Ks, right? So evaluated different Ks and picked one. There's nothing to do that you can, for instance, consider 3, 4, and 5, and then together, for instance, come up with a different method that it's better. Usually, most methods pick one. Okay? But for instance, if you have a machine learning method, you can try to combine them. So they're just vector representations that you can mix and match and not even consider all of them. So for this, you can consider all possible ones. So let's say if you have a camera of size 3, how many we have for a protein, or actually a DNA sequence? We have how many different cameras? The other way around, 4 to the 3. Yeah, so 64. So it has 64. You can consider all 64. You can consider, for instance, only the unique ones. You can consider like this, only the ones you actually saw on the sequences. It's not guaranteed they're going to see the 64 ones. So this has to do basically on your approach and how you model the problem, basically. Yeah, did I answer your question? I'm sorry. And for protein sequences, how many do we have? How many different kamers of size 3 when we consider a protein sequence? 20 to the third? Yeah. Which is 400 times 20. Yeah. 8,000 or something like that? Yeah. So that's going to generate, if you consider all possible ones, and you only have 2 sequences, and you have a kamer of size 3, you're going to have a very, very sparse vector. So if you have, for instance, we're going to have, I'll look later on machine learning methods, but calculating Euclidean distances on a very, very sparse vector is not a good idea, right? So it depends on how you model things and how you compare them, basically. And if we generalize for kamers of size K or N, how many different kamers do we have? N to the K. Yeah. And so basically, distance-based approaches, they rely on this agglomerative hierarchical clustering. And basically, most of the algorithms will start with each data point as a single cluster, each sequence gene separate on a single cluster. And iteratively, we're going to join them into bigger cluster until we reach one big cluster with all the data points. And this generates our hierarchical clustering, which is our tree. And there are different ways that we can actually join them. So the main difference between methods is actually how do we join these clusters together? What's the decision to see, okay, which are the 2 that we are going to put together, and then what are the next steps, and so on and so forth. And for that, we have different variations of methods. For instance, we have single linkage, complete linkage, the one we're going to discuss, which is an average linkage, UPGMA, and neighbor join, for instance. And the main variations is which are the next cluster to merge. And the rationale, for instance, if we take into consideration average linkage, would be, let's first compute a pairwise distance into a distance matrix D. So basically, pairwise distance between all the items we have, all the sequences we have, and we have a matrix here. Those distances could be scores from pairwise alignments. It could be an Euclidean distance from a kamer vector count. Okay? Next, then, we'll find 2 clusters that have 2 clusters or sequences that have the smallest distance, D, I, and J. We'll merge them together and create a different node. So I and J now are connected by a internal, yeah?
I'm sorry for asking so many questions.
That's okay. That's a place for it.
How do you make a representative sequence of a cluster to be able to pairwise align with the other maybe sequences, individual sequences still, or at that stage clusters themselves? So like you join the first two clusters,
Yeah.
sorry, the first two sequences,
Yep.
and you have a cluster and the rest are just individual sequences.
Yep.
How can you then compare that cluster with the other individual sequences?
That's one of the difference between them, between the approaches. So I'm going to talk about next up with average linking, which is UPGMA, which is basically a arithmetic average of your cluster items with all the other items. Okay, you can do different things, which is the next slide. Okay, that's okay. Feel free to ask away, not a problem. So basically, for average linking, we're gonna just find on that matrix the smallest distance, put them together, create an internal node. So I and J are now connected via a new internal node U, and we then need to define the height of those trees, which have to do with the evolutionary time. In this case, for average linking, we'll have the average of the distance between them. Okay, this is just a convention for average linking. And you can consider that, and this considers that both edges have the same height. And next up, we need to update the matrix. So on the next round, our matrix will have one less column, one less row, because we merged two items together. And then we need to then calculate for each k that's not I and j, a new distance for them. So basically, we're calculating a new, so removing two rows and columns and adding another one. Yeah? And then going back to finding the smallest ones. And I put in red here the two main things that vary between these two. One is how do you put the actual heights of the tree, and what you define and how you cluster them. For average linking, you're interested in the smallest distance. For neighbor joining, you want a neighbor that is not always the smallest distance. Okay? So this is the main difference between them. And this will affect the assumption in how the final tree is going to look like. So let's say, so the questions here is, between the different methods is, which are the next clusters to merge? Let's say we have this cluster, IG, we just created. So I is a sequence, J is a sequence, and we have G, which is a new cluster here, right? And they have a distance IJ. And we want to recalculate the distance matrix. So I have a new node here, K, that I need to calculate the distance between K and this new group, which is your question. How do I calculate distances between a node, a sequence, and a group of sequences? And so DKG, which would be then the distance between a item and a cluster. If we consider single linkage, that's basically the minimum between the distance between K and I and K and J. Simple as that. The minimum distance between this cluster and this item is the minimum individual one. Okay? Complete linkage will have the maximum distance. And average linkage would have, any guess? The average, yeah, okay? And that's if you have two items, right? So you have a I and J, you have two items, you get the average, which means you're basically defining a centroid between I and J and calculating the distance between them, okay? And UPGMA is a type of average linkage algorithm that will consider then the arithmetic mean between items of two groups. And one important thing on UPGMA, which is a terrible acronym, is the branches have the same evolutionary rate. So it's considered, it's very appropriate when you consider molecular clocks. Okay? We're going to discuss that in a bit. And neighbor joining does something neat, which is just transforming the original distance to account for different rates of evolution. That's the main difference between them. So if you can't consider the same evolutionary rate, you can't use UPGMA. That's the basic thing. So UPGMA, which is that crazy acronym there, which is an average linkage method. So similar to every other method, all the items will start in separate groups. You need to then keep updating the matrix. every time you merge groups or items together. And for that, you're going to consider the mean distance between existing groups. Okay? And actually the mean distance between elements of each group, which will be something like this. Okay, let's try to interpret this. So let's say we have a group A and a group B, and this represents the number of elements in A, the number of elements in B, and I'm basically summing up all the distance of all pairs between A and B. So X belonging to A and Y belonging to B, we're calculating the distance between them and summing it all up, and I'm considering an average. All right? So if you have two sequences, I will have something like this. So two sequences is just the average between the two. If we have two groups, we'll consider then the distance between all items of this group with all items of this group. We'll get an average. Okay? It's a very simple approach. And this will generate then a tree that looks like this, which is a rooted tree. And it's also a ultrameric or ultrametric tree. I think there's a typo there. And that is to say that all branch lengths between root and leaves are the same. So the values on the branches between root and any of the leaves will be the same. And that has to do in how we label them. And the result of the tree is not guaranteed to be optimal, but it's kind of scalable. So it's a cubic complexity. Why is it cubic? Why is that cubic? So if you consider that in each round, we need to identify what's the closest one. The closest one is basically iterating through a table. Iterating through a table, what's the cost? Finding the smallest element in a table of size n times n, which is quadratic, right? And you're repeating that process until you have a single cluster. And you're potentially doing that n minus 1 times. That's why you have a quadratic cost. So the molecular clock hypothesis I mentioned that it's considered by UPGMA is that all mutations occur in the same rate in all 3 branches. So that therefore you have the same distance from root to leaf. And they also assumes that all branches have the same evolutionary rate. And the rate of mutations in each position along the sequence, it's consistent as well. And this is suitable, therefore, for closely related species and for molecular clocks. For instance, molecular clocks have been used to assign taxonomy, which you consider a gene that you don't expect much variation in terms of the evolutionary rates between positions. For instance, the 16S ribosomal RNA, which has been used. And but if you're not comparing ribosomal RNA sequences, and you expect that in different positions of the sequence you have a different mutation rates, and then this is not appropriate. For instance, if you're considering enzymes, that's not appropriate anymore. Why? Would you expect any part of the enzyme to have a different mutation rate than the other part? What would be that? What do enzymes have to actually perform their function? Yeah, you can say it. Yeah, active sites. Active sites are basically what enzymes use to reduce, to actually perform the catalytic activity, and they tend to be more conserved than the rest of the protein. So you don't expect them to have the same evolutionary rate. And basically, the overall UPGM algorithm is like this. I know it's a lot, so bear with me. So basically, we're going to start with the distance matrix D, all items in separate groups. We'll choose the smallest one in terms of the distance, so Dij being the smallest one, create a new group, connect them with an internal node, and then we're going to set the branch length as the half of the distance between them. So let's say if the distance between them was 5, each of the branch lengths will be 2.5. Okay? Then we are going to calculate the distance between the group and all the existing ones. that is necessary, for instance, to update the distance matrix, then we'll remove those two from the distance matrix and add the new one. And we repeat this process. So if we do maybe iteratively with this example, it will be easier to understand. So let's say we have A, B, C, and D, and this is scoring matrix. No idea where it came from. It could be an MSA, it could be a K-mer count, for instance. And these are the main steps we need to do. So first thing, what's the smallest, what's the shortest distance between any pairs would be between A and C, which is 7. So I'm basically going to join A and C with an internal node. I'm going to set the branch length as the half of the distance, so it's 7, so it's 3.5 and 3.5, and then I'm going to update the distance matrix. So I need to compute the distance between the new group, AC, with the other elements, which are B and D. So computing the distance between B and AC, and D and AC, which is basically computing the distance between B and A and B and C. And we have 8.5, D and A and D and C, and we have 11.5. And we end up with an updated matrix with one less row, one less column. And now we have a group here, which is AC. And we repeat the process. The smallest pair, which is B, and AC, which is 8.5. So we're going to merge, B with AC. And we're going to assign half of the length for each of the branches. So 8.5, so we have 4.25 here. This should be 4.25. Since we already have 3.5, this branch needs to be 0.75. Okay? Remember, because we're considering that any path between root and leaf should have the same height, which is the sum of the branches. And we keep going on until we finish the process. Okay? So it's a fairly simple algorithm. And the main assumption, as I mentioned, is that the rates of evolution are the same among different items and among different positions in the same sequence. So you shouldn't use these methods if you don't have this assumption on your data. Okay? An alternative would be neighbor joining, which is probably the most widely used distance-based method for phylogenetic reconstruction. Is quite used for other methods based on character reconstruction to generate an initial tree, because it's quite quick to run. And then the tree can then be refined. So it does not assume the molecular clock, so you can actually have branches of different sizes on the same cluster. And similarly to UPGMA, you construct a larger cluster C, merging to nearest clusters A and B, but in this case, nearest doesn't mean the smallest distance, because neighbor joining has an extra constraint, which is I want the minimum distance between A and B, and the maximum distance between these and the other clusters. So we are looking for nodes that are close to each other, but also far from everything else. Okay? And to do that, we basically subtract the average distance between each of the nodes we're considering to all other leaves, which compensates for long edges. So on neighbor joining, we expect that the distance between things we just merged together be smaller than distances between things that are far apart from each other. And it's also the same complexity, because then we need to iterate through distance matrix multiple times. So it's an iterative method that keeps adding new clusters together. And in this case, it generates an unrooted tree. And we're going to see why. And slightly more complicated algorithm, but also starts with each node on a different cluster. And then we start off calculating the average distance, UI, between the node I and all the other sequences. And then we're going to try to minimize this distance. So when we're looking at the matrix, we're trying to minimize the ij minus ui, uj, where the ij is the distance between I and j, minus ui, which is the distance between I and the rest of the nodes, and the distance between j and the rest of the nodes. So what we're doing here is finding the nodes that are close to each other and far away from everything to start off building the trees. And we do the agglomerative clustering approach here. And then we compute the distances and create, every time we join two nodes, we create an internal node. And then replace I and j from the distance matrix. And continue until we have only two nodes. And graphically, neighbor joining will work like this. So we start with a star tree. A star tree is composed by a internal node and all the external nodes on the border. And the first thing that we're going to do is we'll keep resolving pairs until they're complete. It's an iterative process. So let's say we consider f and j the first pair to be merged. And every time we merge them, we create an internal node. So fj gives rise to the node u. And let's see that the next node would be e. And that will create an internal node v, which will connect them. So the main reason why this creates an unrooted tree, so instead of putting them connected to f or g, I connected it to an internal node. And I keep doing that process until we connected everything. And of course, we need to keep updating the distance matrix in that process. And for that, neighbor join does not assume that the sequences, lineages, items evolve at the same rate, which is quite important. So the main advantages of distance-based methods would be then they're quite simple, they're flexible, they're easy to implement. You can use different distances, different clustering algorithms to achieve that. And they're usually fast and scalable in comparison to the other methods, which are character-based. For instance, as I mentioned, neighbor join is usually a first step to create an initial tree for refinement for, let's say, maximum likelihood approaches. And the main limitations for distance-based metrics would be then their sensitivity to distance and clustering chosen. Of course, if you change how you calculate the distance, you're going to change the tree you end up with, and if you change the clustering approach as well. And evolutionary rates are not estimated. We have a distance, we put a value that is a weight on the branch, but not actually the evolutionary rate. And there is no measure of uncertainty for the tree obtained. So it's not a statistical method that say, how confident are you with that tree? And just to finish off, trees are usually represented. You have a chance to actually play around with different tree construction algorithms next week. And most of them are represented what's called a Newick file format. Usually when you create something new, you try to be quite creative with the name. And this is a terrible choice of name. It's just, Newick is just a seafood restaurant in the US. And it's basically a text file that specifies a tree. For instance, if you consider this tree here with 5 elements. So we have 4 external leaves and a few internal elements, and we're going to basically describe them as nested parentheses with the distances and the leaf names. This is basically the Newick file format that we're going to use in different algorithms. And it's basically saying we're going to start with a leaf A, which have a branch length of 0,1, and that's connected to B with 0,2. And these two are connected with this cluster here. So these two are connected with this cluster, and then we create a parenthesis, and this cluster with a branch of 0.5, and then is describe the cluster as well. And that's it for today. On Friday, we're then going to move to more complicated methods for defining phylogenetic trees. This is just an overview. Easily, phylogenetics could be a whole subject for this. So the main purpose is just so you guys have an idea of the different approaches. And I'll end up with a dad joke. Thank you very much.